Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com.
Hello.
Today we are undertaking a deep dive into the experimental study of the photoelectric effect.
Which is a core concept from Unit 11, dual nature of radiation and matter.
Exactly. And our goal is to make this topic so crystal clear and, exam safe that you will remember the key experimental relationships for life.
That sounds good.
So let us start with a very simple question. You know that bright sunlight is intense, right? It contains a lot of energy.
Of course.
But why is it that you can sit under a very bright red lamp for hours and not get sunburned? But even a brief exposure to relatively faint ultraviolet or UV light causes DNA damage and sunburn.
That is an excellent point. I always thought brighter light just meant more heat, more energy.
Yeah.
So intense red light should also cause some effect if it's bright enough. Why does the color matter more than the brightness?
Exactly. That observation. It runs counter to all our everyday intuition about how energy is transferred. Think of modern technology, too. Every solar cell, every image sensor in your phone's camera, it relies on this exact surprising principle.
What's that?
That light energy depends on its color, its frequency, and not its brightness or its intensity. This paradox is what the photoelectric experiment was designed to solve.
Okay, so this one effect is behind so much of our tech.
It is. So the core idea is this. Physics in the late 1800s found that light and matter, well, they refused to behave according to the classical rules. The photoelectric effect is the emission of electrons from a metal surface when light shines on it. But the key finding, the absolute game changer, is that this effect depends on the frequency, which is the color of the light.
And not the intensity or the brightness?
Precisely. So the individual energy unit of light is more important than the total amount of light being shown.
Right.
Let's use an analogy. The concert door. Imagine electrons need a certain minimum energy to escape the metal. We call this the work function, or W.
Okay, minimum energy.
Think of it like a concert entrance having a height requirement. The height requirement is the photon frequency.
I see. So a single high-frequency violet photon is what?
It's like a tall, well-built person who can enter instantly, but 50 low-frequency red photons are like 50 short people.
So no matter how many of them show up, even a high intensity.
Exactly. No matter how many arrive, each individual falls below the height requirement and cannot enter. The door remains locked. The visual image here is the energy threshold. Picture the metal surface as a cliff edge that electrons must jump off.
Okay.
Red light is like gentle waves lapping at the beach. No jump. Violet light is like a powerful hammer.
It gives an instant launch.
An instant launch. Now that we have the core idea, let's understand the precise experimental steps that actually confirm this. We'll look at the setup used by Hall, Wachs, and Lenard, which figure 11.1 in your textbook depicts. It's an evacuated glass tube with a photosensitive plate C.
That's the emitter.
And a collector plate A. We apply a potential difference between C and A, and we can use a commutator to reverse the polarity. We measure the current flowing, the photocurrent, using a microammeter, and the potential using a voltmeter.
So we have to control three things: frequency, intensity, and the potential difference.
Yes. But how exactly did they measure the fastest speed of the ejected electrons?
That seems like the hardest part.
That is the crucial part. We apply a negative, or what we call a retarding potential, to the collector plate A.
So we're trying to push the electrons back.
We are opposing their motion. We gradually increase this negative potential until the photocurrent drops completely to zero. This minimum negative potential is called the cutoff or stopping potential, which we denote as V0.
Can you give me the exact definition from the insert source for that, for the stopping potential?
Yes, but please read the definition. It's very important for exams.
Okay, it says, for a particular frequency of incident radiation, the minimum negative retarding potential V0 given to the plate A for which the photocurrent stops or becomes zero is called the cutoff or stopping potential.
Excellent. And so the maximum kinetic energy, or Kmax, of the photoelectrons is related to this stopping potential by the equation.
Kmax equals E times V0.
Correct. Kmax equals EV0. So now we can measure the energy of the fastest electrons. Now for the first key result, they varied the light intensity while keeping frequency and potential fixed.
Okay.
And they found the photocurrent is directly proportional to the intensity of incident radiation.
That makes sense. More intense light means more photons, so more electrons get ejected per second.
It does make classical sense. But here is where the classical theory failed completely. If we repeat the experiment with a higher intensity light, say I2 is greater than I1,
Yes.
the saturation current, the maximum photocurrent increases. just as you'd expect.
What?
But the stopping potential, V naught, remains exactly the same.
Wait, what? That can't be right.
It is.
But if the light is brighter, it's delivering more total energy. The electrons should come out faster.
And if they were faster?
Then Kmax would be higher, and you'd need a bigger V naught to stop them, but it stays the same.
It stays exactly the same. This is critical. The maximum kinetic energy of the photoelectrons is independent of the intensity of the incident radiation.
So brighter light just gives you more electrons, not faster electrons.
You got it. Each electron is only dealing with one photon at a time. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now, the third and most important finding was the effect of frequency. When we vary the frequency of the incident light, the stopping potential, V naught, it changes linearly.
Well, linearly, how so?
A higher frequency, let's say 3 is greater than 2, which is greater than 1.
Like going from red to green to blue light.
Yes. This requires a greater negative stopping potential. So V naught 3 will be greater than V naught 2, and so on.
So if you plot V naught versus the frequency, you should get a straight line.
Yep. You get a perfect straight line. And this means that Kmax varies linearly with frequency. And crucially, this plot reveals that there exists a minimum cutoff frequency, the threshold frequency, below which no emission occurs.
Even if the light is extremely intense.
Even then, the door stays locked. Let's take a quick, simple example to cement the concept. Suppose we use sodium metal. It has a low work function. W is about 2.3 eV.
Okay.
If we shine green light of energy, say 2.48 eV on it, the electron escapes. The excess energy becomes kinetic energy.
So Kmax would be 2.48 eV minus 2.3 eV, which is 0.18 eV.
Exactly. And because Kmax is equal to E times V naught, the stopping potential V naught required to stop these electrons is simply
0.18 volts.
just 0.18 volts. This measurable small voltage is a direct confirmation of Einstein's equation. These experimental facts, the existence of the threshold frequency, the linear dependence of Kmax on frequency, and its independence from intensity.
They couldn't be explained by classical wave theory.
Not at all. These results demanded the radical idea of light quanta, leading directly to Einstein's photoelectric equation. Kmax equals high minus W. Now, let's look at some silent killers, the tricky misconceptions that cost students marks in the exam.
I think I already fell for one.
Misconception 1. Ke in intensity. Many students incorrectly assume that brighter light, higher intensity means faster electrons. They think, just like you did, that brighter light delivers more total energy, making the electrons more energetic.
But we just learned that intensity is independent of V naught, so that must be wrong.
Absolutely correct. Remember the rule. Intensity affects the number of electrons, the photocurrent, but frequency controls the energy or speed, the Kmax.
Okay, so the kinetic energy of individual electrons is determined by the energy of just one photon, high, not the number of photons hitting the surface.
Perfect. Now, misconception 2, the linear plot. Students often forget which variable makes the graph linear. They try to plot V naught versus wavelength.
Oh, that's a mistake, because all is C divided by he, so it's an inverse relationship.
So what would the graph look like?
It would give a hyperbolic curve, not a straight line. We must plot the stopping potential V naught versus the frequency.
Very good. Always plot V naught versus E for a straight line graph. To ensure these facts stick, let's lock them down with some anchors. The most critical relationship is the linear one between stopping potential and frequency.
Okay.
Let's use this memorable phrase. Plot it straight. Voltage versus frequency. Slope is Planck's baby. Intercept is the work.
I like that. Slope is Planck's baby. Reminds us the slope is h over e, which gives us Planck's constant.
And the intercept is the work.
The x-intercept is the threshold frequency, E naught, which gives you the work function W equals h times naught.
It's a solid way to remember. Now for a physical gesture, take one hand and sweep it gently from your lower left up to your upper right.
Okay, like drawing a rising line in the air.
This mimics the linear graph of V naught versus heat. Then use the index finger of your other hand to point exactly where that line crosses the horizontal axis.
That's the threshold frequency in naught.
Exactly. This physical connection helps memory. So, to summarize the experimental study of the photoelectric effect in 3 exam-safe bullets. First, for light above the threshold frequency, the photoelectric current is directly proportional to the intensity of the incident light.
More light, more current. Simple.
Second, the maximum kinetic energy, Kmax, of the photoelectrons, which we measure by the stopping potential, V naught, is independent of the light intensity.
But it increases linearly with the light's frequency.
But it increases linearly with the light frequency, yes. And third, a threshold frequency exists, which is a characteristic of the metal below which no photoelectric emission takes place.
No matter how large the light intensity is.
No matter how large. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is PROFSam, right?
Yes, ProfSam.com. Keep studying hard, and remember that even the most complex phenomena, like the dual nature of light, are built upon simple, observable experimental facts. All the best.